We're starting in section 3.4, solving exponential and log equations, and I want to show you or remind you how to solve exponential equations algebraically, and then show you how to go about solving them graphically. So let's begin with example number 1. I know this is an exponential equation because the variable x is in the exponent. Remember, when the bases of the exponents are the same, we know the exponents are equal. So I'm first going to check and to see if it's possible to rewrite 27 to base 3. So I know that 27 is 3 to the third power. We can double check that mentally. 3 times 3 is 9. 9 times 3 is 27. So it is possible to make the bases the same. And now the bases are same. The exponents are the same. So x is equal to 3. And of course you can double check 3 to the third power is 27. So in example 1, we were able to make the bases the same. In example 2, let's try again to make our bases the same. On the left-hand side, we have 3 to the x power, and on the left, we have 9 times the cube root of 3. I know that 9 is 3 squared, so I can rewrite 9 with base 3. I know that the cube root of 3 can be rewritten as 3 to the 1/3 power. So it is possible to make our bases all 3. On the right-hand side, we do need to multiply these two factors before we can set our exponents equal to one another. Recall that when you multiply like bases, you perform that multiplication by adding the exponents. So we would add 2 plus 1/3, which is 2 and 1/3. So now that the bases are equivalent, our exponents are equivalent, x is equal to 2 and 1/3, or if you prefer, you're welcome to rewrite that as 7/3. Example number 3. Solve exponential equations, again, algebraically, but we're also going to add a graphic component to this equation. Let's first look at solving it algebraically. The base on the left is e, the base on the right is 7. We know that e is approximately 2.718, our natural number, and so it's not likely that we could mentally make the bases the same. So in this case, when you cannot make the bases the same, we can use some of the properties that we've learned in order to isolate x. To get x out of the exponent, we can take the natural log of both sides, so the natural log of e to the x and the natural log of 7. Now remember, we're allowed to do anything we want to an equation as long as we keep our work balanced. Because we took the natural log of both sides, the work we did here is agreeable. So now let's evaluate. The natural log of e to the x, the base of the natural log is e, the base of our exponent x is e, so we can simplify this to x is equal to the natural log of 7. Natural log of 7 has no variables, it is a constant, so if we raise e to the natural log of 7 power, that should give us the value of 7. Let's use our calculators to check that value. In order to confirm that e to the natural log of 7 is 7, and press enter, and yes, it is equal to 7. This is one way to solve an algebraic equation where the bases are not the same. And again, when the bases are not the same, we take the natural log of both sides. I want to also show you how to solve graphically. We know that, and let's go back to the original equation, e to the x equals 7. So I'm going to rewrite the equation, e to the x equals 7. and I'm going to substitute y in the place of both sides. Y equals y. Okay, is the equation y equals y a true statement? Yes, it's true. So now I'm going to show you that I can rewrite this as y equals e to the x and y equals 7. I could have used any variable. I'm choosing y because I'm preparing to graph this function, and in order to graph it I want it to be equal to y, so we think in terms of an x-y coordinate plane. Okay, so I want you to take a moment and pause the screencast, and on this coordinate plane graph e to the x and then graph y equals 7. Okay, so I've graphed e to the x power and y equals 7. We can see that those two equations intersect at this point. Well, this point has an x-coordinate. I don't know exactly what it is. I know that that x-coordinate falls between integers 1 and 2. And I know that it has a y-coordinate of 7. But I do not know what the corresponding x-coordinate is. So let's graph this on our graphing calculators and trace to find that specific point of intersection. So remember, add a graph, and we're going to put two equations on the same page. So y equals e to the x. And then to make the equation bar open again, you would select tab, and it opens a new equation bar, and this is y equals 7. Now, according to my screen, I can't see that. My screen only goes up to 6.67. So your settings may be different. So we'll go to menu and zoom, and I'm going to zoom out just a little bit, and now I can see that point of intersection. So a couple ways you can find this value. You know, of course, you can trace until we get there. Remember, we are looking for a y coordinate of 7. And by tracing, it's hard to get exactly on it, but if we finally got there, 2.1 is the x coordinate. If I don't want to use trace, you can go back to menu, analyze graph, and you're looking for the intersection point. So again, slide this finger to the left of the intersection point and to the right of the intersection point. And this time, it looks like it's giving me 1.95 rather than 2.1. I would say that the intersection is going to be more accurate than the trace, because the trace sometimes is rounding your y coordinates. Now, how can we double check to see whether we should use 1.95 or 2.1? Well, we can calculate that. So let me go to a calculator, and I will raise e to the 2.1 power, and I see that it's actually 8.17. That's not accurate. If I raise e to the 1.95 power, I get 7.03. So I will say that 1.95 is the most accurate. So using the graphical method, I want you to use the intersection function rather than using the trace function, because the trace didn't come out to be quite as accurate as we would like. Also, you could double check to see if the natural log of 7 approximates to 1.95, and let's check that out. And it does approximate to 1.95.